and you have to calculate percent error. So this is two problems in one. First, you're going to have to do the density calculation to see what density your data is telling you. And then you're going to have to compare that to the accepted value. What is the equation for percent error that you must know from now until the time you're done with science?
Observed value minus accepted value divided by accepted value times.
Right, good. So our percent error is the observed value, that's what you get, the experimental value sometimes it's called, minus the accepted value, which has to be given because it's in a test question, so I have that information for you, divided by the accepted value times 100. And please remember that this is absolute error, so you're taking the absolute value of this. You're not going to have negatives. Okay? Not going to have negatives. Okay? 30. You are calculating the mass. I'm going to give you the density, and instead of giving you volume, I'm going to give you length, width, height. So what are you going to do with the length, width, height? Multiply them together to get what? The volume. And then what are you going to do? I'm giving you density and length times width times height. Then you have to find the mass. Okay? So this is another one that is a couple problems that we had in the body of the test as separate problems, now put together into one. 31. Awesome question. Explain why significant figures are necessary for measured quantities. Be specific. Here is the test question for those of you that chose to participate today. Explain why significant figures are necessary for measured quantities. Okay? Why do we need to worry about these sig figs? That is the burning question.
For what?
For measured quantities. Why can't we just do our calculations and write down everything the calculator spits out? Why isn't that right? You don't have that many decimals where? On your measuring device, your measuring instrument. Your fancy schmancy calculators will spit out 10 or 12 decimal places. And mathematically those numbers are fine. But we don't have a balance that goes to 10 or 12 decimal places. We don't have a ruler or graduated cylinder or thermometer or burette or any other measuring device that can be that specific or that precise. So we can't have all those extra numbers in our answer. We need significant figures to help us figure out how to round and figure out the limitations of our measuring device. 32 is an awesome question. You have to draw. Okay? And I've had this density column here for a while, and it's kind of blended together. We lost our yellow. We're sort of losing orange. But when this started, it was a rainbow. Red, orange, yellow, green. There was a blue, and there was actually indigo and violet, but because it's hard to do in food coloring, the whole bottom looked kind of the same. This is sugar water, and it's of different concentrations. It's plain old red water at the top, and it's really, really syrupy water with a lot of sugar in it at the bottom. Okay? And every color was a different concentration, which made it a different density. So this is an example of a density column. And on the test, you are going to have a spot to draw that is going to look like this, only neater. Okay? And then you're going to have a big data table with lots of different substances. Pine is 0.4. These are all in grams per centimeter cubed. Water, 1.00 grams per centimeter cubed. Oil, bricks, feathers, sodium chloride, whole bunch of different things, probably about a dozen or so. And we're going to ask you about 6 of them. We're going to ask you about 6 substances from this data table that has a lot. And we are going to ask you to draw them in the density column wherever they would end up. So if I said, out of this list, bricks, feathers, water. Bricks, feathers, water. Where would they go in this density column? Bricks on the bottom. So we'd have bricks sitting down here, right? Then what?
Water.
Then water. Then what? Feathers. Okay, you're just going to have to pretend those are feathers. All right? And you'd have to show what would layer where. So if we had these 6 different substances and we dumped them all into a container like this, where would they all settle out? And you're going to have a drawing like this.